In this video, we're going to talk about improper integrals. Now, improper integrals are integrals that are like these. Now, notice we're integrating, so on this first example, not from some number to another number, so like integral from 3 to 7 of e to the negative x dx. We're integrating from 0 to infinity. Okay, integrating from 0 to infinity. This one we're integrating from negative infinity to infinity. This one we're integrating from 2 to infinity. We have something from negative infinity to 0. So these integrals are called improper integrals. Okay, when you're integrating out to infinity. Now, you can have other types of improper integrals. For example, if you have something like a vertical asymptote. So for example, at x equals 5, at the left endpoint here, this one has a vertical asymptote. Okay, and this one has a vertical asymptote at x equals 2. That's within this interval over which we're integrating. So these are all examples of what are called improper integrals. Now let's begin with an example. Now this example is not an example of an improper integral. This is just an ordinary integral from 1 to 10 of the function 1 over x squared. So I've drawn the function 1 over x squared right here. Okay, and the question is, what's the integral from 1 to 10? Now, notice, since this is a non-negative function, what we're really talking about here is what's the area underneath the function, okay, between 1 and 10. Okay, so let's do this. If we want to integrate 1 over x squared, we write it as x to the negative 2 power. And integrate x to the negative 2, we get x to the negative 1 over negative 1, which is the same thing as negative 1 over x, right? Because x to the negative 1 is the same thing as 1 over x to the positive 1, and this negative here can come out front. Okay, but we're going to evaluate this from 1 to 10, so we plug in 10 for x, and then we subtract what we get when we plug in 1. So we get negative 1/10 minus a negative 1, that's like negative 1/10 plus 1, which ends up being 9/10 or 0.9. So this is 0.9 square units. Okay, 0.9 square units, that's that area. Now let's change this up just a little bit. What if we integrated from 1 to 100 of the same function? So instead of going 1 to 10, we go 1 to 100. Well, how much area are we going to add? Notice this is really, really close to the x-axis, but obviously we're going to be adding some area if we're integrating from 1 out to 100. So what is the area if we integrate from 1 to 100 to the same function? Well, notice when we integrate, we still get negative 1 over x, but this time evaluated from 1 to 100, so we get negative 1 over 100 plus 1. So that's 99 over 100, or 0.99. Okay, now you can imagine what would happen if we went 1 to 1,000. Okay, I think we would get 0.999. Okay, or what if we went 1 to 1,000,000? We'd get something like 0.999999. Okay, so notice though, what would happen if we went from 1 to infinity? Okay, so what we're talking about really is what's the total area underneath this function from 1 all the way out to infinity. Now I've actually drawn the function right here. So the area underneath this function from 1 all the way out to infinity. Now notice this gets really close to the x-axis. You may expect though that the area has to be infinite, right? Because you think, oh man, this goes on this way forever. You might expect, oh, the area's got to be infinite. Well, it turns out in this case, the area is not infinite. So what do we mean when we say integral from 1 to infinity? Well, what we really mean is we're going to integrate from 1 out to some number b, and we're going to take the limit as b approaches infinity. By the way, you can use whatever letter you want there. Sometimes I use the letter k instead of the letter b. The book uses b because they like to think about this as the integral from a to b. Okay, but to integrate from 1 to infinity, it's like integrating from 1 to b, and then taking the limit as b approaches infinity. So notice what happens. We have the limit as b approaches infinity of this. Okay, but we integrate x to the negative 2. We end up getting negative 1 over x. But this time we're plugging in b. Okay, instead of 10 or 100, we're going to plug in b for x. But then we're going to take the limit as b goes to infinity. So notice what we have here is negative 1 over b plus 1. Okay, remember when b was 10, we end up getting negative 1/10 plus 1. Or when b is 100, we ended up getting negative 1/100th plus 1. Okay, but what if we let b approach infinity? Well, as b approaches infinity, this approaches 0. So what we get is 0 plus 1. So amazingly, the area there is 1. The total area underneath this function from 1 all the way out to infinity, the total area is only 1 square unit. Okay, it's not infinitely many square units. It's not an infinite area. It's actually a finite area, which is pretty amazing. okay, because it has like an infinite length here, but it's getting so close to the x-axis so fast that actually when we integrate to 10, we get 0.9. We integrate out to 100, we get 0.99. Integrate out to 1,000, we get 0.999. It's going to get, that area is going to get closer and closer to 1. Okay, so that's pretty amazing, okay, that this improper integral converges. In fact, here's our definition here. The improper integral of f over the interval from a to infinity, okay, where a is just some number, is defined to be, well, the integral from a to infinity of f of x dx is just the integral from a to b of f of x dx, only we take the limit as b approaches infinity. Okay, so integrating from a to infinity is like integrating from a to b and then letting b approach infinity. Okay, in the case where the limit exists, like in that last example, the improper integral is said to converge. Okay, and the limit is defined to be the value of the integral. So our limit over here ended up being 1. Okay, so the integral there is 1. Okay, in the case where the limit does not exist, the improper integral is said to diverge. So sometimes, if you integrate it all the way out to infinity, you get an infinite area. Okay, and in that case, we'd say that the integral diverges. Okay, so notice, we're integrating here from a to infinity. We're looking at what's this total area right here. Okay, so let's do a couple examples. What's the integral of from 2 to infinity of 1 over x cubed? Okay, we could draw the graph of 1 over x cubed. So change this up. There's 1 over x squared. By the way, what does y equals 1 over x cubed look like? Okay, well, there it is. Okay, notice they cross there at 1 comma 1. But 1 over x cubed looks like this. Okay, so what's the total area underneath this function from 2 to infinity? Well, we're going to integrate from 2 to b and let b approach infinity. Now remember, 1 over x cubed is like x to the negative third, and if we integrate x to the negative third, we get x to the negative 2 over negative 2. Okay, evaluate it from 2 to b, and then the limit as b approaches infinity. Now, I realize it's kind of a pain to keep having to write limit as b approaches infinity over and over again, but you really should do that. And by the way, don't just write these things that are all disconnected. Make sure you have equal signs between these, right? Okay, you're giving an argument that you want the reader to understand. Okay, so when you plug in the b and the 2, well, before we plug those in, let's actually simplify this. X to the negative 2 in the numerator can become an x to the positive 2 down here. And this negative can actually come out in front of the fraction. Okay, but if we plug in b and then subtract what we get when we plug in 2, we get negative 1 over 2b squared minus a negative 1 over 2 times 2 squared. And don't forget both of these negatives. It's a minus minus. So what we get is negative 1 over 2b squared plus 1/8. Okay, that's 1/8 there. Okay, but remember, we're taking the limit as b approaches infinity. As b approaches infinity, this goes to 0. Okay, now if the b squared had been on the top, as b approaches infinity, that would blow up to infinity. Okay, but since b squared is in the denominator, as b goes to infinity, that goes to 0. So this is 1/8. So the total area underneath that curve from 2 all the way out to infinity is only 1/8 of a square unit. Okay, so if we integrate this function, okay, 1 over x cubed, let's write it here. From 2 all the way out to infinity, so from here all the way out that way, forever, it's only 1/8 of a square unit. Okay, now what about the integral of 1 over x? Okay, and let's do it from 3 to infinity. Well, the integral of 1 over x from 3 to infinity, we can integrate from 3 to b and take the limit as b approaches infinity. Now remember, the integral of 1 over x is natural log of the absolute value of x. Okay, so if we plug in b and plug in 3, we get natural log of the absolute value of b minus natural log of the absolute value of 3. Now, natural log of 3, or the absolute value of 3, that's just some crazy decimal. But if we take the limit as b approaches infinity, natural log of b actually blows up to infinity. Okay, the bigger b is, the bigger natural log of b will be. And as b goes to infinity, this goes to infinity. So we get infinity minus some constant, which is really just infinity. So what this means is this integral diverges. Okay, so it's kind of amazing. Here's 1 over x cubed. What would 1 over x look like? Well, 1 over x looks like this. Okay, now notice it does get closer and closer to the x-axis here, the further and further we go to the right. But it doesn't do it fast enough so that you get a finite area. Believe it or not, the area underneath this green function, 1 over x, is infinite as we go further and further to the right. Okay, you can integrate from 1 to 100 or 1 to 1,000 or 1 to 1,000,000, and it's infinite. Now, let's see, I think I started at 3, but whether you start at 1 or 3, if one way of doing it gives you an infinite area, the other way of doing it will give you an infinite area, right? If you integrate from 1 to infinity or 3 to infinity, this little area here is not going to affect whether the total area is infinite or not. Okay, so notice what we have here is that this integral diverges. Okay, you may not expect that. You might think, oh yeah, it's going down to the x-axis here, so therefore it's got to be a finite area. But it turns out it's not. Okay, it's infinite. Okay, now what about 1 over the square root of x? Okay, so now let's graph. We have 1 over x cubed right there. What about 1 over the square root of x? Now the square root of x is really x to the 1/2 power. Okay, but notice 1 over the square root of x is in purple here. Well, notice if the area underneath this green function is infinite, okay, then the area underneath this purple function, okay, all the way down to here, that should be infinite as well because it contains this area. Okay, so I expect our integral to be infinite. Now, underneath the blue one, that was actually a finite area. Okay, but the area underneath the green one and the purple one are going to be infinite. So let's actually check that. Okay, so the integral of 1 over x, the square root of x, is like integrating x to the negative 1/2 power, because x to the negative 1/2 is like 1 over x to the positive 1/2. In other words, 1 over the square root of x. Okay, we're integrating from 1 to b and taking the limit as b approaches infinity. The integral of x to the negative 1/2 would be x to the positive 1/2 over 1/2, or in other words, 2 times x to the 1/2. Or 2 times the square root of x. Now if we plug in b for x and plug in 1 for x and subtract, this over here just ends up being 2, right? 2 times the square root of 1. But then we have 2 times the square root of b, and we're going to take the limit as b approaches infinity. And as b approaches infinity, the square root of b will also approach infinity. So again, what we get is that this integral is infinity, or in other words, the original integral diverges. The area underneath that curve from 1 to infinity diverges. In fact, here's a theorem, and you can prove this theorem. It's not too hard to show. If we take different values of p and we integrate 1 over x to the p, so for example, 1 over x to the 1, which would just be 1 over x, or 1 over x squared, or 1 over x cubed, or 1 over x to the 1/2 power, right, the square root of x, this will converge if the p is bigger than 1. Okay, so if the p is 2 or 3 or 7 or even like 1.5 or 1.1, the area underneath that curve, 1 over x to the p, will converge. Okay, and it will diverge. It'll be an infinite area if the p is less than or equal to 1. So if p is 1, that's the case where we have 1 over x, and when we integrate, we get natural log of x. But if p is less than 1, so maybe p is 1/2 or 2/3 or something, it will diverge. And by the way, I've drawn in here, this was from the book here, 1 over x. The area underneath 1 over x is actually an infinite area. Okay, but the area underneath, that's the blue one. The area underneath the green one and the purple one, those are actually finite areas, right? Because our p here is 2 and 3, it's bigger than 1. If we did 1 over x to the 1/2 power, that function would be up here. Okay, and that would also have an infinite area from 1 to infinity there. Okay, so it's maybe a good idea to graph on Desmos or whatever, 1 over x to the p for different values of p. Okay, let's look at another example. So what if we integrated from 0 to infinity of e to the negative 5x power? Okay, well, e to the negative x looks like this, so e to the negative 5x looks something like this. Okay, and the question is, what's the area underneath this curve from 0 all the way out to infinity? And notice this gets down to the x-axis pretty fast. Now, it never actually touches the x-axis, but it gets closer and closer to the x-axis really, really fast. So the question is, what's this total area underneath this function? Okay, is it a finite area or is it an infinite area? Okay, well, let's do it. Integrating from 0 to b is like integrating from 0 to infinity is like integrating from 0 to b and letting b approach infinity. Okay, and then the integral of e to the negative 5x. Remember, the derivative of e to the negative 5x would be e to the negative 5x times negative 5. The integral of e to the negative 5x ends up being negative 1/5 e to the negative 5x, or in other words, e to the negative 5x over negative 5. Okay, and if we plug in b, oh, by the way, e to the negative 5x is like 1 over e to the positive 5x. Okay, if we plug in b and plug in 0, what do we get? We get negative 1 over 5 e to the 5b minus a negative 1 over 5 e to the 5 times 0. Now 5 times 0 is just 0, and e to the 0 is 1. So what we get is 1 over 5 times 1, so that's 1/5. So we have a minus a negative 1/5, so that's positive 1/5. Now here, as b goes to infinity, e to the 5b blows up, right? That goes up to infinity. So 1 over that should go to 0, right? As b goes to infinity, this goes to 0. So what we get is 0 plus 1/5, or 1/5. In other words, 0.2. Okay, the total area underneath that function from 0 out to infinity is only 0.2. Okay, it's not infinite. It's actually a pretty small number, 0.2. Okay, let's do one more example of this. Integrate from e to infinity, 1 over x times natural log of x quantity cubed. Okay, so how can we do this? Well, again, instead of integrating from e to infinity, we integrate from e to b and let b approach infinity. Okay, then we're going to have to do a u substitution. So this is not obvious how to do this necessarily, but if we let u be natural log of x, the du is the 1 over x dx. So what we can do is write this as the 1 over x dx, that becomes the du. And what we're left with down here is e cubed, or u cubed, right? That u is ln of x. Now I changed these limits of integration because we did a u substitution. This e and b are really x values. Okay, they're associated with the dx. If we want to change them to u values, how do we do that? Well, notice when x is e, look at u equals ln of x. When x is e, what's u? Okay, well, ln of e is 1, right? When x is e, u would be ln of e, which is 1. So that's why I changed this to 1 here. Okay, now when x is b, what's u? Well, u would be ln of x, but if x is b, it would be ln of b. Okay, so u would be ln of b. So we're going from 1 to ln of b. So again, that's a little weird to change those. You could decide to keep them the same, but then you'd have to go back to x's in the end. Okay, so let's integrate 1 over u cubed. Now this is not going to involve a natural log. If it were just 1 over u, it'd be natural log of u, or natural log of the absolute value of u. But if it's 1 over u cubed, remember we write it as u to the negative 3. And to integrate u to the negative 3, we do it as u to the negative 2 over negative 2, which is the same thing as negative 1 over 2u squared. Okay, so again, it's kind of a pain to have to keep writing this limit as b approaches infinity, but please do that every time. Otherwise, what you're writing won't be correct. And also connect your answers by putting equal signs between it. Okay, then finally plug in ln of b for u and plug in 1 for u and subtract. So we don't have to go back to x's because we changed our limits of integration here. Okay, so if we do this, we get negative 1 over 2 times ln of b squared minus a negative 1 over 2 times 1 squared. Okay, now this is just negative 1/2 here, and we have it's being subtracted, so we have a negative 1/2. It's positive 1/2. And here, as b approaches infinity, ln of b will approach infinity. Okay, so ln of b quantity squared will approach infinity, so the whole denominator will. So that fraction as a whole will approach 0. Okay, it's always key. As b approaches infinity, a lot of times you'll get something either approaching 0 or approaching infinity. You have to kind of check. Okay, and so notice what we get is 0 plus 1/2 or 1/2. Okay, that's the total area underneath this curve. Okay, and I've drawn the curve here, y equals 1 over x times ln of x cubed. And remember, we're integrating from e out to infinity. Now, e is between 2 and 3. So we're integrating from this number, 2.718 here, all the way out to infinity. What's the total area underneath this curve? And that's what we found. By the way, this does have a vertical asymptote over here at x equals 1, because when you let x be 1, ln of x is 0. It also has a vertical asymptote at 0, okay, because of this. Okay, but we're integrating from 2.718 from e out to infinity. We get that area, and remember what our answer was. Our answer was 1/2. Okay, now we could have improper integrals where we integrate from negative infinity to b. Okay, negative infinity to some number. And the way we define that is instead of going from negative infinity to b, let's just go from a to b and let a approach negative infinity. Okay, so again, if we're going to integrate from negative infinity to b, let's just integrate from a to b and let a approach negative infinity. Okay, and again, the integral is said to converge if that limit exists, and it's said to diverge if it doesn't, right? So like if you get an infinite answer or something. Now, finally, there's also improper integrals where you integrate from negative infinity to infinity. And the way you do that is you integrate from negative infinity to some number c plus the integral from c to infinity. And if both of these integrals converge, then this integral will converge. But if at least one of these integrals diverges, this one will diverge. And by the way, the c could be any number that you want. Okay, the c could be 0 a lot of times what we do. So instead of integrating from negative infinity to infinity, we integrate negative infinity to 0 and 0 to infinity. But really, it won't matter what your choice of c is. When you sum up these two integrals, you should get the same thing. Okay, if they both converge, when you sum them up, you should get the same thing no matter which c you pick. Okay, so the improper integral is said to converge if both of these integrals converge. And what do we mean by this integral and this integral? Well, we've already talked about how you integrate out to infinity or from infinity to c. Okay, and this integral, original integral, diverges if at least one of these diverges. Okay. Oh, that was the wrong picture right there. But okay, let's look at an example. So suppose we want to integrate from negative infinity to 0 of the function e to the 3x. Okay, so let me graph e to the 3x right here. So y equals e to the 3x, e to the 3x. Okay, notice this is what the integral looks like. Here we want to integrate from negative infinity up to 0. So instead of integrating from negative infinity up to 0, let's integrate from a to 0. And then we'll let a approach negative infinity. So it's kind of like we're integrating from negative 10 to 0, negative 100 to 0, negative 1,000,000 to 0. We're just integrating from a to 0, but letting a approach negative infinity. Okay, so how do we do this? Well, again, integral negative infinity to 0 is like integrating from a to 0 and letting a approach negative infinity. Now the integral of e to the 3x is 1/3 e to the 3x. Okay, integrated from, evaluated from a to infinity, or a to 0, I'm sorry. Plug in 0 for x, and then subtract what you get when you plug in a. Now e to the 0 is just 1, so this whole first term is just 1/3 times 1, or 1/3. And as a approaches negative infinity, this approaches 0. Okay, now if a approached infinity, this will blow up to infinity. But as a approaches negative infinity, notice if a is like negative 10, this would be e to the negative 30th. But that's a tiny number because it's like 1 over e to the 30th. Okay, so as a approaches negative infinity, this approaches 0. So we get 1/3 minus 0, which is 1/3. So that total area is just 1/3. Okay, now what about an example where we integrate from negative infinity to infinity? Okay, of something. So 1 over 1 plus x squared. So let me graph 1 over 1 plus x squared. In fact, here's the graph right here, 1 over 1 plus x squared. It looks like a bell curve, has a bell curve type shape. We can integrate this from negative infinity to c, and then from c to infinity, only I'll just let c be 0. It makes it as easy as possible if you let it be 0 in this case. Okay, so what are these two integrals equal to? Well, I claim that both of these integrals, they're each pi over 2. So that the total area underneath this is actually pi, right? It's kind of amazing. The total area underneath this bell curve shape here is pi. Okay, now how do we do this? Well, let's do some scratch work. What is this integral here? What's the integral from 0 to infinity of 1 over 1 plus x squared dx? Well, again, instead of integrating from 0 to infinity, we integrate from 0 to b and let b approach infinity, positive infinity. And what's the integral of 1 over 1 plus x squared? Isn't it tangent inverse of x? Okay, tangent inverse of x. And we're evaluating from 0 to b. So we plug in b and we plug in 0 and subtract. Now tangent inverse of 0 is 0. But what's the limit as b approaches infinity of tangent inverse of b? Okay, well, I've drawn the graph of y equals tangent inverse of x, okay? And the question is, what happens as we go further and further to the right? What's tangent inverse of 6? What's tangent inverse of 10? What's tangent inverse of 100? What are those things getting closer and closer to? Well, it turns out this gets closer and closer to pi over 2. Okay, and this really makes sense if you start thinking about triangles and tangent inverse, right, as x gets bigger and bigger and bigger. Okay, and by the way, also it has another horizontal asymptote at y equals negative pi over 2, okay, down here. Okay, but as we go further and further to the right, it gets closer and closer to pi halves. So tangent inverse of 8, it's pretty close to pi halves. Tangent inverse of 100 or 1,000,000 is going to be really close to pi halves. So notice if we come back here, what's the limit as b approaches infinity of tangent inverse of b? Well, that's going to be pi halves. Okay, like tangent inverse of 100 or 1,000 or 1,000,000, it's getting closer and closer to this. So we have pi halves minus 0, which is pi halves. And by the way, you can do the same thing integrating from negative infinity to 0. Okay, so really, we're splitting up this area here into two pieces. I found that the area to the right of the y-axis, right, from 0 to infinity, this area is pi halves. It's going to turn out this area is pi halves, and you can kind of see it because it's symmetric, right, with respect to the y-axis. Okay, but if you actually do the integral, you'd be integrating, instead of negative infinity to 0, you'd integrate a to 0 and let a approach negative infinity. You end up getting the same type of thing here, only you have a 0 here and an a there. You have tangent inverse of 0 minus tangent inverse of a. Tangent inverse of 0 is 0. The limit as a approaches negative infinity of tangent inverse of a, that's going to be negative pi over 2. Right? That's as we go further and further to the left. But we have a negative pi over 2 that becomes pi over 2. Okay, so notice this integral is equal to this one plus this one, but both of those were pi halves, and so the total area underneath that curve is pi. Okay, so this is an improper integral. Now, we can also have improper integrals due to vertical asymptotes. So here we're not going to integrate from like a to infinity, from like 5 to infinity, or negative infinity to 7, or negative infinity to infinity. We're just integrating between two numbers, okay, maybe integrating from 3 to 7, but we maybe have a vertical asymptote right here. Okay, this is what's called this is also an improper integral. Okay, so integrating from a to b, how do we do that? Well, to integrate from a to b, what we're going to do is integrate from a to k, and then take the limit as k approaches b. Now, k is going to approach b from the left. Okay, k is not going to approach b from the right. So integrating from a to b will be the same thing as integrating from a to k, but then taking the limit as k approaches b from the left. Okay, so if f is continuous on the interval a to b except for an infinite discontinuity at b, so just like these situations. Okay, now the vertical asymptote could be way up here, or it could be down this way. Okay, but then the improper integral of f over the interval from a to b is defined to be this. So again, integrating from a to b is like integrating from a to k, and then taking the limit as k approaches b from the left. So that negative really means from the left. Okay, so this happens, you have to do this if you have a vertical asymptote like this, or you have an infinite discontinuity at the b. Okay, in the case where the limit exists, we say the integral converges. So if we end up getting a finite number here, an actual answer, we say the integral converges, or it could be that you have an infinite area here. Okay, so in which case we say that the integral diverges, right? If that limit doesn't exist, the integral diverges. Okay, so let's look at an example. Okay, what's the integral from 0 to 1 of 1 over the square root of 1 minus x? Now I've graphed 1 over the square root of 1 minus x. Notice it has a vertical asymptote at 1. Okay, if you plug in 1 there, notice you get a 0 in the denominator. 1 over 0 is like it's infinite. Okay, and it's not the whole, I haven't graphed the whole function here, but just between 0 and 1, the question is, what is this area? Okay, is it a finite area, or is it an infinite area? It certainly looks like the area is bigger than 1, because this right here is 1 square unit right there. Okay, but I don't know, maybe it's 2 square units, maybe it's infinitely many square units. Okay, we don't even know whether it converges or diverges. So how do we do this? Well, again, instead of integrating from 0 to 1, we integrate from 0 to k, and then take the limit as k approaches 1 from the left. Okay, now how would you integrate 1 over the square root of 1 minus x? You can write this as 1 minus x to the negative 1/2 power and do a u substitution. Right, if u is 1 minus x, du is going to be negative dx. So notice we have a u to the negative 1/2 power, but we have to put that negative in there. Okay, and also we can change the limits of integration. The 0 and the k, those are x values. So if x is 0, what's u? Okay, well, u would be 1. So that's why I changed this from 0 to 1, right? Because if x is 0, u is 1. Okay, now if x is k, what's u? Well, if x is k, u would be 1 minus k. Okay, so that's how we change it from k to 1 minus k. Okay, well, you can integrate u to the negative 1/2 to u. It's u to the positive 1/2 over 1/2, which is the same thing as 2 times the square root of u. Right, u to the 1/2 is the square root of u, but we're dividing by 1/2, so that's like multiplying by 2. Okay, so we evaluate it from 1 to 1 minus k, and we still have this negative out front. So we plug in 1 minus k for u, plug in 1 for u, and subtract. Notice what we get. We still have this negative out front here, but as k approaches 1, notice what happens. Well, as k approaches 1 from the left, this is going to be 1 minus 1, that's 0. So we have 2 times 0 essentially right here. But then this is really just 2 times 1, that's 2. So we have really 0 minus 2, and there's a negative out front, so we have a negative 2, which is positive 2. So actually, we had a pretty good guess here. So this was 1 square unit. It turns out down here, turns out all this part up here ends up being 1 more square unit. So this whole area is 2 square units. Okay, so this integral converged. Okay, it converges. And the integral, we say it converges to 2. Okay, or the value of the integral is 2. Okay, now we could have a similar thing on an interval from a to b where we have an infinite discontinuity at the left endpoint at a. Okay, so if we have an infinite discontinuity at a, at the left endpoint, like a vertical asymptote there, instead of integrating from a to b, we'd integrate from k to b, and then we take the limit as k approaches a from the right. Okay, and again, the integral will converge if the limit exists, and it will diverge if it doesn't exist. Okay, that's the definition. Okay, so let's do a couple examples. So if we integrate from 0 to 8 of 1 over the cube root of x, what do we get? Okay, well, let me draw the graph here. So here's 1 over the cube root of x, right? This is x to the 1/3 power, or the cube root of x. We want to integrate from 0 up to 8. So 8's way over here. But notice at 0, we have this vertical asymptote there. Okay, so the question is, what's the total area underneath this curve from 0 all the way out to 8? Well, again, we have this infinite discontinuity at 0. So what we can do is integrate from k to 8. So just pick some k right here. Integrate from k to 8. And take the limit as k approaches 0 from the right. Okay, so integrating from any value of k that's bigger than 0, so like 0.2, let's say, all the way up to 8, that integral makes sense. We already know how to do that. But to integrate from 0 to 8, we have to integrate from k to 8 and let k approach 0 from the right. Okay, so that's what we've done here. Now remember, integrating from 0 to 8, it's like integrating from k to 8 and taking the limit as k approaches 0 from the right. Okay, again, we have that vertical discontinuity there, or infinite discontinuity at 0. Okay, vertical asymptote. Okay, now to integrate 1 over x cubed, write it as x to the negative 1/3, and the integral of x to the negative 1/3 is going to be x to the positive 2/3 over 2/3, right? We have to lift this number up by 1, and negative 1/3 plus 1 is 2/3. Okay, so this is really 3/2 x to the 2/3 power, evaluated from k to 8. Then we take the limit as k approaches 0 from the right. So we plug in 8 and plug in k and subtract. Now 8 to the 2/3 is going to be 4, because you take the cube root of 8, which is 2, and you square it, which is 4. So we have 3/2 times 4 minus 3/2 times, well, notice as k approaches 0, k to the 2/3 will approach 0, right? So this is really 3/2 times 0. Okay, so limit as k approaches 0 from the right of k to the 2/3, that's 0. So we just get 3/2 times 4, so that's 12/2 minus 0, which is really just 6. And does that make sense based on our picture? Is the total area underneath here 6? Yeah, that looks reasonable. Okay, like up in here, that's not adding much area way up there. But this total area right in here from 0 all the way up to 8, yeah, that could be about 6 square units. If you imagine each one of these is 1 square unit, this block right here. So the area, yeah, it looks reasonable at least. Okay, now what about the last case? If f is continuous on an interval a to b, except for an infinite discontinuity at a point c. Okay, within the open interval a to b. Okay, so you have an infinite discontinuity not at the left endpoint a or at the right endpoint b, but somewhere in the middle. Okay, then how do we do this improper integral? So notice here, if we want to integrate from a to b, but there's this infinite discontinuity at c. Okay, so how do we do this improper integral? Well, essentially what we do is just integrate from a to c and then integrate from c to b. And we already know how to integrate from a to c, because that's when we have a vertical or an infinite discontinuity at the right endpoint. We've already talked about that. We already know how to integrate from c to b, because that's when we have an infinite discontinuity at the left endpoint. Okay, so the improper integral of f over the interval a to b, okay, this interval from a to b of f of x dx, is the integral from a to c of f of x dx plus the integral from c to b. Okay, where the two integrals on the right side are themselves improper. The improper integral on this side here, this is said to converge if both of these converge, and it's said to diverge if at least one of them diverges. Okay, if either one diverges or both, this original one is said to diverge. Now you have to be a little careful here. I'll give you a little warning in a second here. But how would we integrate from 1 to 4 of 1 over x minus 2 to the 2/3 power? Okay, so I've graphed y equals 1 over x minus 2 to the 2/3 power here. And notice we have a vertical asymptote at x equals 2. So if we're going to integrate from 1 to 4, we have to be a little careful. Okay, we can't just do the fundamental theorem of calculus like we normally do, because the fundamental theorem of calculus assumes that you have a nice continuous function on this interval from 1 to 4. But we don't. We have a vertical discontinuity here. So we have to recognize that this is an improper integral. Okay, so instead of integrating from 1 to 4, we're going to integrate from 1 to 2, and then add that to the integral from 2 to 4. Okay, and the way to do the integral from 1 to 2 is we're going to integrate from 1 to k, and take the limit as k approaches 2 from the left. And then to integrate from 2 to 4, we're going to integrate from k to 4, and take the limit as k approaches 2 from the right. Okay, you don't have to pick the letter k. In fact, if you use k over here, maybe you should use a different letter over here. Okay, it doesn't really matter though. Okay, so notice we're integrating from 1 to 2, that function, plus the integral from 2 to 4, that function. So you have to recognize there that you have that vertical asymptote. Notice that value of 2 makes the denominator be 0. So we have an infinite discontinuity there. Okay, now I'm going to do some scratch work to figure out these integrals. The first one, the integral from 1 to 2 of 1 over x minus 2 to the 2/3 power. Again, we're going to integrate from 1 to k and take the limit as k approaches 2 from the left. Okay, and to integrate this, remember this is x minus 2 to the negative 2/3 power. You could do a u substitution if you want, or maybe you can do it in your head. The integral of x minus 2 to the negative 2/3 is going to be x minus 2 to the positive 1/3 over 1/3. Or in other words, it'll be 3 times the cube root of x minus 2. Okay, evaluate it from 1 to k. So if you plug in k and then you plug in 1 and subtract, what do you get? Well, notice we're taking the limit as k approaches 2. Well, as k approaches 2, this is going to approach 0. Okay, so we get 3 times 0. Now what about this? 1 minus 2, you might think, oh, that's going to be imaginary. But, well, if you have the square root of negative 1, it's imaginary. But we have the cube root of negative 1. And the cube root of negative 1 is negative 1, right? Negative 1 times negative 1 times negative 1 is negative 1. Okay, so this is the cube root of negative 1, which is negative 1. So notice we have 3 times 0 minus 3 times negative 1. So it'd be 0 minus a negative 3. That's positive 3. So this is 3. So what that really tells us, according to the picture, is that the integral from 1 to 2 here, this area here, to the left of this, vertical asymptote. So let me draw in the vertical asymptote there, x equals 2. Okay, between x equals 1 and x equals 2, this area is 3. Okay, now this area between here and 4, it looks like it's a little bigger. In fact, it's kind of symmetric here. The integral from 1 to 2 looks like it'll be the same as the integral from 2 to 3. But we're actually not integrating just from 2 to 3, we're going 2 to 4. So I expect this area over here to be a little bigger than this area right there. And it turns out it is. Okay, if you work out the details, instead of integrating from 1 to 2, you integrate from 2 to 4, and you take the... You do the integral from k to 4 and take the limit as k approaches 2 from the right. If you work all this out, here you have the cube root of 4 minus 2, and that's the cube root of 2 times 3, and then again as k approaches 2, this will approach 0. So we get 3 times the cube root of 2. Notice that's bigger than 3, because the cube root of 2 is bigger than 1, right? So 3 times something a little bigger than 1 should be bigger than 3. Okay, so if you work this out, you get 3 plus 3 times the cube root of 2. You can factor out the 3 there and write this as 3 times 1 plus the cube root of 2, which ends up being about 6.78. Okay, so that's about 6.78 square units is what this total area is going to be. Now, one last thing I want to mention, it's a little bit of a warning, is notice what can go wrong if you try to apply the fundamental theorem of calculus directly to an improper integral without using the appropriate limits. So let's suppose we just kind of cavalierly approach this. Oh, integral from minus 1 to 5 of 1 over x squared dx. Now, here's the graph of y equals 1 over x squared. Okay, it looks like this. So if we're integrating from minus 1 to 5, okay, it looks like we're getting some area underneath here. Okay, notice the function's always a positive function above the x-axis. So we're looking for the area here. We don't have to worry about like a net signed area or anything. Okay, so what do we get? Well, if we kind of cavalierly approach this and just think, oh, let's just integrate from 1 to 5 of x to the negative 2. Integral of x to the negative 2 is x to the negative 1 over negative 1. And then let's rewrite this as negative 1 over x. If we plug in 5, plug in negative 1, we get negative 1/5 minus a negative 1 over negative 1. There's a lot of negatives there to deal with. But notice what we get is negative 1/5 really minus a positive 1. So that's negative 1/5 minus 1. That's negative 6/5 or negative 1.2. Now, that answer can't possibly be correct. Negative 1.2. By the way, it doesn't look like we made any mistakes along here, right? But that can't possibly be correct. It's a negative number, right? Our answer should not be negative because we're integrating a non-negative function on this interval from 1 to 5 here. So we shouldn't expect to get a negative answer. I mean, if our function were down here, we could maybe we could see that. Maybe we have it's below the x-axis. We get a negative area because we're talking about a net signed area. But there's no way this answer should be negative. So what went wrong? Well, what went wrong, and the reason this is incorrect, is we did not take into account the fact that this has a vertical asymptote at x equals 0. Okay, so we can't just integrate from minus 1 to 5 like this. We have to integrate from minus 1 to 0, and then do the integral from 0 to 5. Okay, and if we do that, it turns out if we do that, what happens? Well, if we integrate from minus 1 to 5 of 1 over x squared, it's like integrating from minus 1 to 0 of this, and then integrating from 0 to 5 of this. So let's do the second one first. What's the integral from 0 to 5 of 1 over x squared? Well, it's like integrating from k to 5 and taking the limit as k approaches 0 of 1 over x squared, which is x to the negative 2. Now, x to the negative 2, when you integrate, it's x to the negative 1 over negative 1, which is negative 1 over x. If we plug in the 5 and the k, notice what we get. We get negative 1/5 minus a negative 1 over k. So it's really negative 1/5 plus 1 over k. But notice we're taking the limit as k approaches 0. Not as k approaches infinity, but as k approaches 0, this is going to blow up to infinity. So what we get is negative 1/5 plus infinity. That's just infinity. So actually, we don't even need to worry about this integral here. This area is infinite. And so therefore, if at least one of these diverges, remember, this one diverges. So the correct answer to this integral is not, oh, it's negative 1.2, which is what you might expect if you think, oh, let's just do the fundamental theorem of calculus. Bang, 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 bang. Okay, it turns out, though, the answer is infinite. Okay, the integral diverges. So what went wrong? Why didn't the fundamental theorem of calculus work? Well, one thing you have to remember about the fundamental theorem of calculus is the fundamental theorem of calculus only works if the function is continuous. Okay, the theorem assumes that your function is continuous over the integral over which you're integrating. But notice, is the function continuous from 1 to 5 here? Well, it's continuous from, or negative 1 to 5. It's continuous from 2 to 5. Okay, but from negative 1 to 5, notice it has this vertical asymptote here. So actually, the fundamental theorem of calculus doesn't actually apply. So you can't just do the antiderivative and plug in the endpoints. You actually have to break it up. You have to recognize it's an improper integral. Okay, so be careful of this. I tend to put a question like this maybe on a quiz, and so check it out. And by the way, notice we didn't even have to calculate this integral because if this one diverges, then no matter whether this one converges or not, this thing is going to diverge. And by the way, I think this one also does diverge. Now, one other thing I think is really interesting, I think there's a problem in the book that has to do with this. If you look at the function 1 over x, okay, so there's 1 over x squared, but let's look at the function 1 over x. Okay, it looks like this. Okay, and let's just go from 1 to infinity. So let me look at x equals 1 to infinity and take the portion of the graph that's under the function 1 over x from 1 to infinity. If we were to take this and revolve it around the x-axis, okay, kind of like when we were doing our solids of revolution, we revolve this around the x-axis, what you would get is something that looks like this. Okay, only it would just continue on to the right forever. Okay, so it's sometimes called Gabriels Horn, right? It looks like a horn. Okay, like from a trumpet or something, but it just goes on and on and on forever. One thing that's really interesting is if you try to calculate the volume of this horn, it turns out the volume of this horn is a finite volume. Okay, so integrate. So remember how you find the volume? Okay, I think you'd use the disk method. So you'd have something like pi times your f of x squared. So it'd be pi times the quantity 1 over x squared. Okay, and then you integrate from 1 to infinity, but the way you do that is to integrate from 1 to b and take the limit as b approaches infinity. Or you could call it k or something, but whatever you want to call it. Turns out you're going to have a finite volume. Okay, it's not infinite. You'll actually get a finite volume. Now, if you try to do the surface area, though, using our surface area formula, okay, way back from earlier in the semester, turns out you have an infinite surface area. So that's really weird. This has a finite volume, but an infinite surface area. Now, it's been suggested, and the book mentions this, that if you could kind of fill this horn with paint, let's say, you could fill it with a finite amount of paint. And if you let the paint kind of seep through this surface, it turns out you could actually paint an infinite surface with a finite amount of paint. Okay, a finite volume of paint. Okay, so that's really crazy. So I don't know. What do you think about that? That's it's kind of paradoxical, actually. So anyways, this is a really interesting example. So definitely try the homework problems for this section. And this topic is improper integrals. And it's going to be a very important integral for when you start in on Calculus 3 and you do sequences and series and you do infinite series. You have to do improper integrals quite often. So this is an important section.